All right, Advanced Math 8, here we go. We've got lesson 3.1.4, defining rigid transformations. So you're going to need your resource page for this one. This resource page starts here. This is for the first problem. And I've got 8 different ones that they want you to do a transformation on. And we're just going to kind of go a little bit deeper into the transformations and notice some things about what stays the same and what changes about the shapes when we move them. So first one, it wants us to rotate clockwise 180 degrees. Now, this one, they don't have the coordinate plane, but you can pretend that the axes are going right through this point. So let's do it 180 degrees. So I'm going to start here. 180 degrees this direction would mean right here for this point there. This point here, 180 degrees, would end up being right there. And then, let's see, this point would stay in the same spot. This point, 180 degrees, so it's back 1, up 3, so it's going to go over 1, down 3, 1, 2, 3. Going to show up there. This point is back 1, 2, 3, up 1, 2, 3, so we're going to go 1, 2, 3, 1, 2, 3. There's that point. This point, 1, 2, 3, 4, 1. So we're going to go 1, 2, 3, 4, 1 right there. And then this point is just going to go straight back this direction 3. So here's our shape. All right, so that's going this direction 180 degrees. All right, now they want us to go 180 degrees this direction. So this one stays in the same spot. This one, we go this way 180 degrees, and that point ends up being right here. This point goes 180 degrees and ends up being right here. This one, 180 degrees, I think that was 3, 3, so 3, 3, ends up being right there. This spot, 180 degrees, so that's 1, 3, so 1, 3, ends up being right there. This spot, it's going to go whoop, right to there. And then this one is going to go whoop, right to there. And so, here's what we got. All right, next one. We want to go 90 degrees this direction, so clockwise. Okay, so 90 degrees. If I spin that 90 degrees, remember you can spin your paper 90 degrees to see where it's going to end up. So this one looks like it will end up right here. This one right here, it's back 1, up 1, 2, 3. So I would go 1, 2, 3, up 1 right there. So that one becomes this right here. This one goes up 1, 2, 3, 4. So I'm just going to go over here 1, 2, 3, 4. So there's the next section right there. This one goes over 1, up 1, 2, 3. So I'm going to go 1, 2, 3, down 1. Right there. And then these connect here. Okay, so there's 90 degrees that direction. Next, we're going to go 90 degrees this direction and see if anything changes. So if I go this direction, this one is going to go whoop right to here, spin 90 degrees. Remember, you can spin your paper to see where it's supposed to end up being. This one is 1, 3, so I'm going to go 3, 1. This one is up 1, 2, 3, 4. So going this way, it's going to be 1, 2, 3, 4. And then this one is 1, 3. So I'm going to go 1, 2, 3, 1. And there's our new shape. All right, so there's the first 4. Next, this one wants to go 270 degrees this way. That's a lot. So I want to go 270. So this point's going to go 1, 2, well, 90, 180, 270. So it'll show up there. This one right here will go 90, 180, 270. Is it 3? Yeah, 3. This one goes 90, 180, 270. And then this one goes, let's see, it's going to go, what's that, 3? So this one's going to go 90, 80, 180, 270. Nope. Up one. Oh, I missed with this one. Dang it. Oh, I was spinning around this point, not this point. Oh, sorry. This one should have been here and this one should have been here. I wasn't looking. So those aren't correct. And then this one's going to end up being here. All right. I probably should have been watching what I was doing, but I wasn't. All right, next one. Maybe I shouldn't use green. Green's too close to that other color. All right, anyways, now we're going to go 360 this direction. Wait a minute, 360, 190, 180, 270, 360. That's going to be on top of itself. And if I do this one, it's going to be 90, 180, 270, 360. That's going to be on top of itself. 90, 180, 270, 360. That's on top of itself. So 360, the shape's just on top of itself. Nothing changed. All right. This one, 180 degrees. Doesn't give me a direction. I don't think it matters. Because if I take this one, 180 degrees, so this is point A, what I notice here is this is 1, 2, 1, 2, 3. So it's 2, 3. So this would be -2, -3. This point would end up over here. This would be A prime. This point is 1, 3. So we'd go -1, -3. This would be B prime. And if we look at all of our points, this point here shows up as this point here. This point here shows up as this point here. And so on and so forth. If this one is spun 180 degrees, it's just on top of itself. Nothing changes. Now, if this one is spun 90 degrees, it doesn't give us direction, so let's try 90 degrees this way. If I go that way, A, 90 degrees, let's see, it's 2, 2, so 2, 2. This would end up being A prime. It'd be on top of itself. Every single one would just go click over. Look, if I spin 90 degrees, it's the same shape. If I spin it back 90 degrees the other way, same shape still. All right. So let's go ahead and look at what our conclusions are from this. So for A and B and D and C, does counterclockwise and clockwise matter? Okay, let's look at A and B. When I did 180 clockwise and then 180 counterclockwise, did it matter? No. So it looks like for 180 degrees, counterclockwise and clockwise don't matter, and we probably already knew that. So 180 degrees clockwise and counterclockwise doesn't matter. Now for 90 degrees clockwise and 90 degrees counterclockwise, does it matter? Yeah, these shapes did not end up in the same spot when we went clockwise and counterclockwise. So 90 degrees does matter. Are there situations where the rotated image lies on top of the original? Yes. So here's our situations. Right here on F, when we rotated 360 degrees, it's on top of itself. So yes, if it's 360, we found out that it's going to be right on top of itself. Now, there are some special situations, like G and H, where if we rotate, they're still on top of each other. Now, this one, if we would have gone 90 degrees, the end would have been like sideways, right? So 90 degrees would have made a new image. But when I went 180, this particular image was on top of itself. And then when we had a square, when we rotated it at 90, it was still on top of itself. When we went 90 the other direction, it was still on top of itself. And if we went 180, it'd still be on top of itself. So, are there situations where the rotated image lies on top of the original? Yes. Always. with 360 degrees, and sometimes with other rotations. So sometimes a rotation does not change its shape, and we're going to get a lot into that in the next section. But for right now, we can just see that 360 always brings us back to where we were, and sometimes 180 and 90 brings you back to where you were, and it doesn't change the shape at all. All right, we're ready to move on. 3-39. So I got a nice little graph for you. It wants us to graph the points 4, 1, 2, 5. So let's go ahead and do that. Let's make a coordinate plane on this one. This looks about halfway. So this is going to be my coordinate plane right here. All right, yay, coordinate plane. All right, so let's go ahead and plot the points 4, 1. So 1, 2, 3, 4, 1. There's A. And then 2, 5. 1, 2, 1, 2, 3, 4, 5. There's B. All right, we're going to rotate this one. So let's make a little line there. All right, so we're going to rotate it 90 degrees counterclockwise. So we're going to go this direction against the clock. Okay, so I'm going to go against the clock. So this is 2, 5. So I'm going to go 1, 2, 3, 4, 5, 2. There's B prime. This one is 4, 1. So I'm going to go 1, 1, 2, 3, 4. There's A prime. All right. Done. And it says label the origin O. There's O for origin. All right, so it says that it wants us to connect A to O. All right, I'm going to use different colors for this. So A to O. I'm just going to make a dotted line here. So A to O is that. Okay, then it wants me to connect B to O. Let's do teal. Ooh, B to O is teal. All right, there's B to O. Can you tell the difference between those two colors? Kind of. All right, and then we want to do A prime to O. So I'm going to do it with the same green because I did A to O with green there. So there's A prime to O. And then I'm going to do B prime to O. So let's go back to the teal. All right, so we've connected them, and what do we notice? Well, here's what I notice. This distance from O to A and this distance from O to A prime looks exactly the same. You know, it goes up 1 over 4, back 1, up 4. That's the same exact distance. So I'm going to say, you know what? I'm going to put a tick mark on there. In geometry, a tick mark shows they're the same. That looks the same. Now, it doesn't look the same as B. B is farther away. But when I look at the distance from O to B, it looks the same distance as O to B prime. So that's the first thing I know. It looks like the distances to the center of our rotation look like they're keeping the same. So A keeps the same distance from O, and B keeps its distance as we're spinning it to O. So those distances stay the same. The other thing that I notice, just look at the two A lines. That really looks like a 90-degree angle. And then the B's, those distances there, those really look like 90-degree angles. So it looks like as we're spinning these objects, we're keeping our distance to the origin, and we're creating right angles when we look at the distances. And it makes sense because didn't we just spin that 90 degrees? And 90 degrees is a right angle. Okay, so we notice that A O is congruent or the same measurement as A prime O. And we notice that BO is congruent or the same distance as B prime O. We also notice that we have some perpendicular lines. It looks like AO is perpendicular to A prime O. And BO, that sounds bad, is perpendicular to B prime O. All right, so it looks like that happened. It says, what's the measure of angle A prime? So A prime. That looks like a 90-degree angle right there. Explain what measurements a rotation preserves. Well, I can tell that AB and A prime B prime are the same length. So it preserves just means keeps the same. It preserves the length of the segment being rotated. And it preserves the distance to the origin. So each point is the same distance to the origin. So A and A prime are still the same distance. So it also preserves the distance of points to the origin. Now remember, we're just spinning around this point. So it makes sense, since we're spinning around it, that we're keeping the same distance. But as we're keeping the same distance, we're also keeping the segment's distance too. So that's what we want to see. We're keeping the same distance to O, and the distance of these segments is staying the same as we do that. All right, so 3-40. This one is straight from that last lesson that we did. On this one, it wants us to connect some other points. It wants P to P prime to be connected. It wants Q to Q prime to be connected. And it wants R to R prime to be connected. All right, so there we've got all of our connections there. What measurements do the reflections appear to preserve? Well, looking at this, it looks like the sides and the angles of these triangles are exactly the same. Like this is the same shape as that shape, right? So what's being preserved? Is the sides and angles of the object being reflected. That's fine, just object. Okay, here's something else that's being preserved. P to the line of reflection is the same thing as P prime to the line of reflection. Q to the line of reflection is the same distance as Q prime to this line of reflection. R to the line of reflection is the same distance as R prime is to the line of reflection. So the other thing that we notice is that the points are the same distance to the line of reflection. When I say points, I'm talking about the matching points. So P and P prime, we call these corresponding points. Q and Q prime, they correspond and they're the same. Now, last thing that I want you to notice is that we're also creating 90-degree angles here. These are all 90-degree angles. How could we prove they're 90-degree angles? If we only did a lesson on this. Oh, we did. How do we prove 90 degrees? Well, we'd look at the slope. This one goes up 1, 2 over 1. So this line right here, that one is up 2 over 1. That's this dotted line, the reflection line. So it goes up 1, 2 over 1. Now let's look at our other lines. So this one goes down 1 and over 1, 2. So that one goes down 1 and over 2. This one goes down 1 over 2, down 1 over 2. So that one is also negative 1 over half, or negative 1 over 2. This one goes down 1 over 2, down 1 over 2. So that one's also down 1 over 2. So what are we noticing? These lines that we created, which are the distances, are perpendicular because these are opposite and reciprocal slopes. So the green, the blue, and the red line are perpendicular to the line of reflection. All right, moving on. Evan has graphed the point 5, 7. Well, Evan, you didn't give me points here, but whatever. All right, so Evan, this is 5, 7, we're going to assume. It'd be nice if you gave me tick marks, Evan, but you didn't, did you? So that's 5, 7. He's got this line right here, which is y equals negative 2/5 x plus 6. And that he thinks that when I reflect it over there, that it's going to be 2, 2. Now, Evan did not give me a lot of information to go on, but he's predicting that when I reflect this, it's going to be a 2, 2. It doesn't quite look right, but we need to prove him wrong in some way. Well, what we noticed before was that we should be perpendicular when we go across. So let's just check if we're perpendicular. So this slope is negative 2 over 5. So the slope right there is negative 2 over 5. Now, we want to be perpendicular because when we cross here, we need to be perpendicular to that line. And the slope that it's perpendicular is the opposite and reciprocal. So opposite means it's going to be positive. Reciprocal means it's going to be 5 over 2. So let's use these 2 points and see if we get a slope of 5 over 2. So I'm going to do the change in y over the change in x. So my y values are 7 and 2, so I'm going to do 7 minus 2. My x values are 5 and 2, 5 minus 2. So I end up with 5 over 3. That is not right because we wanted 5 over 2. So Evan is not correct because the slope between these 2 points is not perpendicular to the line of reflection. So it's not the opposite reciprocal of negative 2 over 5. So he is not correct. No, it would not be there. Because if he was correct, the slope would have been 5 over 2 instead of 5 over 3. All right, moving on. Next section, here it is. 3-42. We're going to describe the transformation. We're going to connect. Describe it first. Okay. Well, it's facing the same way. Let's see. C goes over 1, 2, 3, 4, 5, and then 6, 7, and down 1, 2, 3. So it goes right 7, 1, 2, 3, 4, 5, 6, 7, and down 3. This one goes 1, 2, 3, 4, 5, 6, 7, down 3. 1, 2, 3, 4, 5, 6, 7, down 3. It looks like they're all going right 7, down 3, so that's a translation. Right 7, down 3. All right. Now I want to connect A to A prime. Okay, let's do that one in green because I can. Okay, A to A prime's connected. B to B prime, we'll do that in blue. And then C to C prime, we'll do that in red. All right, what measurements are preserved? Well, the first measurements that are preserved is this triangle and this triangle are exactly the same. So what do we preserve? The sides and the angles of the object are going to be preserved. So AB and A prime B prime look like they're the same. This angle A down here is the same as angle A there. So the preserved is the sides and angles of the object. And then we can see that the distance, look at the distance of the green line, the red line, and the blue line. Those distances look like they're all the same. So the distance between the corresponding points is the same. So the distance from point to point, A to A prime, B to B prime, C to C prime, those ones are preserved. So the distance between the points. Now this is different from the reflection. In the reflection, the distance from the point to the line was preserved. On this one, it's point to point that's preserved. That's preserved, not reserved. Now here's the last thing I noticed. All three of these lines are parallel. Okay, so the lines connecting the corresponding points are parallel. So, translations. Point to point is preserved, and the lines that make point to point are congruent. Reflection. Point to line, that distance is preserved. And then these lines end up also being parallel and perpendicular to the line of reflection. Rotations. Point to rotation, center of rotation is preserved. And in all three of them, they keep the object keeps its side lengths. And when we had a polygon here, the angles kept their measurements. And that happened on the translation, it happened on the reflection, it happened on the rotation. That's why we call them rigid transformations. Rigid means that when we move it, it keeps its side length and it keeps its angle measurement. So everything that we've done with transformations so far has been rigid because the shapes stay the exact same size. All right, 3-43. A's at 3,3, B's at 1,1, C's at 6,1. Give the coordinates of the image of ABC, triangle ABC, after this transformation. Okay, so we're supposed to take the x's and change its sign, and take the y's and change its sign. So A, if I change the sign of the x and the y, would be at -3, -3. That's A prime, sorry. B prime, according to this transformation, we would change the sign of the x and the y. So that would be at -1, -1. C prime, we would change the sign according to this transformation of 6 and 1, so it'd be -6, -1. Now, which two transformations can this represent? Well, the first one, hopefully you remember, is a 180-degree rotation. So this could be a 180-degree rotation. Remember, left or clockwise and counterclockwise doesn't matter. So that's one thing. Or it could be a reflection over the x and a reflection over the y at the same time. So reflect over the x-axis and y-axis. You may be asking yourselves, well, how is it a reflection over the x-axis? Well, when we reflect over the x-axis, the y changes its sign. And when we reflect over the y-axis, the x changes its sign. So if I reflected over both axes, the x and the y would change its sign. So a reflection over the x-axis and a reflection over the y-axis is the same thing as a rotation of 180 degrees. All right, so give the same thing when it looks like this is a translation of left 6 and down 3. So if I took A prime, or A, and did this transformation, we would subtract 6 from the x, so that would make -3. And then we would subtract 3 from the y, and that would be 0. B prime, so I would do 1 minus 6, which would be -5. And I would do 1 minus 3, which would be -2. C prime, I'd do 6 minus 6, which would be 0. And then I'd do 1 minus 3, which would be -2. All right, we have a methods and meaning section for this one. So in our methods and meaning section, remember this is in the book. This is just going to go over what we just did. So if you've missed some of it, this is the information you need to know. They talk about how the reflections, that between the 2 points, it makes a perpendicular line there, and that these A to P and A prime to P are the same distance. For a rotation, it talks about when we rotate, that the distance from P to O and the distance from P prime to O is the same. Also, this angle that's created here, down here, is the angle of the rotation. So this angle from P to O and O to P prime is the same angle as the rotation. So maybe this is like 45 degrees or something like that. Then in translation, we're just sliding the image from Q to Q prime, from this point to this point, this point to this point. We notice that all of these distances of our translation are exactly the same, and all of these distances that we're doing here, they're all parallel to each other when we do a translation. So that's the formal definition of what a rigid transformation is. All right, that was a lot. I'm sorry, I did not know it would last that long. That's all I got, I guess. Okay, do your homework. Bye.